Welcome you all. Today we are going to talk about graphs. Actually, we are going to do some problem solving with graphs. Beforehand, let me explain what is graphs. A graph is nothing. There is vertices like uh, 1, 2, 3, 4, 5. There is vertices and it is connecting them. It is connecting them. Also, there can be this is also a graph data structure. I'm going to deep dive into the various type of graphs. Trees are also some kind of subset of graphs. So what actually we should do is we should master the problem solving with graphs. So before that, this is graph and how computer can understand this, because this is a visual representation for us. There is two main ways to represent graphs to our program. The first one is adjacency matrix, adjacency list, adjacency list, and the second one is adjacency matrix, adjacency matrix. So most efficient and most widely used method is this adjacency list. So what is an adjacency list? So let's look at this example we are taking here. Adjacency list is nothing but there is a list containing all the vertices. For example, there are 7 vertices. So there are 7 lengths, 1, 2, 3, 4, 5, 6, 7 length list. And in each these lists, there are vertices that connected to that particular vertex. If you get example, 1, 2, 3, 4, 5, 6, 7. 1. What are the other vertices connected to 1? It's 3, 4 and 2. For 2 it is 1 and 5. For 4 it's 1, 3 and 5. For 5 it's 2 and 4. For 6 it is only 7. For 7 it is only 6. So this is an adjacency list. When we are actually doing the program, we can implement this like nested vectors, like in C++, nested vectors. So vector inside a vector, I think. So this is a practical way that we implement in when we are programming. Or we can do, since most of the times we know there are how many nodes there are, how many nodes means how many vertices there are, we can make an array for the outer list and a vector for the inner one. So most of the time we don't know how many connections are there, how many edges are there, but we know how many nodes are there. So for this we can use an array, because when we are in C++ or if you're using another programming language, it will be different. But if you're using C++, this is the method. Okay. So adjacency matrix is, what we are doing is we are making a matrix both of into this direction and this direction both have 1 to 7. In this case we have 7. So here also we have 7, and this direction also we have 1, 2, blah 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 7. So if 1 1 is there is a connection between 1 1, of course if there is self loop, uh, we define self loop, we should take this 1 1 as 1. otherwise it will be 0. To 1 there is 3, 4, 2. So there is maybe somewhere here 3, so 3 become 1. And maybe somewhere here 4, so 4 become 1, 2 become 1. So for 2 there is 1 and 5. So 1 and 5 is here. Others are 0. So likewise we are making a matrix and put 1 and 0s towards it. But this method becomes inefficient if there is a lot of zeros. That means there are many vertices but less edges. So we are wasting our memory. So the most common one we use is this adjacency list. There is a more theory concept in this. This is a triangular matrix because it is symmetric around this main diagonal. So and there is some concept like self loops. In some graphs, there is self loop is available. So our main goal is problem solving with this. So if you find a problem like that, we can look at it, which is the best way to master it is solving problems. So now what we're going to do is we're going to implement depth first search. What is depth first search means? For the depth first search, we are using the stack data structure, or there is another method using recursion without using stack. I will go through both of things. And what meaning of DFS depth first search simply is go deeper and deeper. So let me clearly explain this with one example you will get. So imagine this is our graph and this is our stack. So we are going to do the depth first search through this graph. So if you have some kind of confusion, actually I imagine that the input is like adjacency list, impractical adjacency list, so adjacency matrix. So this is the theory part of how we are searching through a graph using depth first search. First, we are starting with some kind of a node. Uh, if we say we start with this one here, this is the initial one. This is the initial one. So we push it to the stack. So one is here. Then we mark this as visited, or I will make it true. Then I go one of the siblings of that node. Let's say 2. I visit here, so I make it true and add it to the stack. Again, in a stack, the pointer is always towards this element, the last element. So we're looking at always the last element in the stack. We're looking at the last element in the stack and go to that element sibling. So the last element is 2, so go to its sibling. It's 9. So I make it true, I mean it's visited, and add it to the stack. So 9 is added. So now I am looking at 9. So I visited some sibling of 9, true, and it's 6. I added to the stack. If there is no siblings to that node, I use an outside one node. What we are doing is we popping that element. So we are popping 6. Now where are we at? We are at 9. So again we are looking at a sibling of this element 9. So this is already visited, true, so we visited 7. True, added to the stack. Again there is no siblings or no child. Child value is not necessary. The siblings to the 7. So I pop 7 again and a 9. So 9. 2 is already visited. I have 3 here. So I visited 3. From 3, now the stack is looking at this element, okay? From 3, is there a siblings? Yes. I visit 4. I visit 4. And from 4, what I do is, I looking at a sibling. That is 5. 5 added to the stack. And 8 added to the stack. From 8 there is no, I pop 8. I again come to the 5. And 5 there is other siblings, yes, 10. From 10, I make it true. From 10 is the other elements without false? No, all are true. So I pop it. From 5, no, I pop it. From 4, no, pop it. From 3, pop it. From 9, pop. 2, pop. 1, pop. So we end up with the empty stack. So that means we visited all the vertices in the graph. Now, what is about breadth first search? In breadth first search, what we are doing is we are searching through level by level. We are also saying that it is level searching. For the breadth first search, we are using queue data structure. So let me explain straight away. We have a queue. Remember in queue, what we are looking at is this front element and also this back element, and we are adding to the back and removing from the front. That is simply meaning. Let me start with some words. Let's say 1. So I visited 1. I added to the queue, and so I add some extra 2 more edges to this because to make some more uh, tiles to this one. So what we are doing is we are starting with a random element, random node, and added it to the queue. And queue is always looking at this element, and queue is always looking at this element, the front element, and we are adding to the back. And we are at one of siblings of 1. Add up, that means 5. So I visited 5 and added to the here. So in stack, even though we add 5, we are always looking at this top element. Okay, that is the nature of queue. So we are again looking at this element. We are always looking at this element and add it simply. So we already added 5, so we added 3. So we now add 3. Is there other elements? No. So what we do is we pop this and come to here. And now we are looking at 5. So 5, we have what are its siblings? 3 already visited, 1 already visited. So pop it and come to here. So 3, what are its siblings? 2, we make it true. And 6, we make it true. The 1 is already visited and 5 is already visited. So pop it, come to the next element. It's 2. From 2 we have 3 and 6 already visited. So pop it and come to the 6. We have 3 and 7. So 3 is already visited. So 7. We visit 7. Is there other elements? No. So pop it, come to 7. Is there 3, 6 and 4? They are already visited. So 4 is only thing we have left. So pop it, come to here. For 4, is there other siblings too? No. So pop it. So we have a queue, empty queue. So I hope you have some idea of about the queue data structure. If you have, this will be good because in a queue what we are always looking at is the top element and we are popping from the top. So graphs are really good to understand. You get a good understanding about the stack and queue. So this is breadth first search. Now let's implement depth first search and breadth first search using C++ because to our problem solving we can use directly those codes. So let's go to the code. So let's go line by line. So first we have to include the IO string. I am using C++, so IO string. And then I have to include because I am using vectors to get adjacency list, and the other needed I need vectors, so I include vectors here. And then I need stack and queue, so I am going to use those libraries too. So stack for the depth first search and the queue for the depth stack for the depth first search and queue for the breadth first search. And uh, I'm going to make a function. Uh, I'm going to make a function depth first search. First I go to depth first search, so I make a function depth first search, and for that function what are coming as parameters is we come with the starting node, start node, because from what node we are starting, so we need the start node, and our adjacency vector. So adjacency vector should not be adjacency matrix. Adjacency list should not be changed. So I will make it const and nested vectors. Vector, vector. So inside those there is integer values. And most importantly, I using pass by reference method, and I make it the name is adjacency. Because I use pass by reference because if you use calling this function several times, uh, in C++, if you don't use this reference, it always make a new vector. It always make a new element. So it will be unnecessary and it will be inefficient. So we can use just const and pass by reference. So it not be changed. And int how many nodes? So total nodes. That means how many vertices are here. So our approach is to make all the elements, all the nodes, all the edges. We visit through all the edges. So we make a Boolean vector with the total number of nodes that we can ensure it we visited all of them. So I use vector, and inside it there is Boolean elements, and I name it as visited, and inside this there is total nodes number of elements, and all are false because uh, until now we didn't go to any element, so all the are false. So this is just a vector with all false. So next, so our main approach, I will tell you our main approach is we have a vector with all are false. So when we are visiting each by each, we make them true to ensure we visit all. Then I have to move the stack object here, stack integer, so that is integers, and I name it as s. And we have our starting node, so remember what we call, we just push it to the stack. So s dot push, we push to the stack what start node. That's the first thing we done when we are implementing by scratch the depth first search. So our loop is, I am going to make a loop, while loop, and that loop is running until our stack is empty, because we know that if the stack is empty, that means we are already visited all the nodes. So if not, s dot empty. Since this is not empty, not node becomes true, so this will work. If this becomes empty at any times, it becomes yes, this will exit from the loop. So, so now we are programming what we are learned. We just make, we just get the top element, because in a stack what we are looking at is the top element. So we make a name for that. Int node is equal to the s dot top. So top. So we are looking at the top element, and what we are doing is we are popping it. We are removing. You will understand why we are popping here instead of at last, because when we go to the end of the code, you will understand. I will explain this. So s dot pop, popping the element. So in a stack, it's from the upward. So it stack is first in, last out, last in, first out. They both are same. So we pop it, but even though we pop it, we have that element inside nodes. So what we're doing is we make sure that this node is not already visited. So what we're doing is if visited, it's an array, we are going to the node. So if this false, this whole become true. So it's okay. We are not visited it. We are not visited it. If we are not visited it yet, but we are doing it, we are make it visited. We are make it visited. Make this not. Uh-oh. Uh-oh. Not is equal true. So he visited. Then if you want to display the output, you can out it here, like you can write like cout, but I'm not going to do it. Okay, I will leave it as a comment. Maybe you can cout to see not, and space for the last word. So okay, so next what we are doing is we are taking how many number of siblings he have. That means this node have. So for that I make another variable int number of neighbors. I take num equal to adjacency. You know, this is a nested tree. Uh, Vector. So I go to the node and dot size. So this is a nested one. So you get how many siblings he has. So it is int num. Then what I do is I make another loop, for loop. For integer, I start with that is num, and I am until it's greater than or equal to 0. I will explain this, and I will decrease it. Then equal to 0, equal to 0, and until it's, and I decrease it. So do you have what idea here what is happening? I want to go deeper towards the tree. So I choose one sibling here. Now I'm going to choose one sibling. That means int neighbor. is equal to the something we are in the node adjacency dot dot I. So I go to one sibling. Here what I done is I go to one sibling of that node, and if it is not visited, okay, if it's already visited, it's not if it's not visited, this node is not visited. If it is not visited, what I'm doing is I push it to the stack. Start push to the stack. Think about the spelling tree. So what now happened? So this for loop is inside this while loop. So in this for loop, what we are doing is we are. So you might wonder, what the hell is this? This is not make a difference. Let me explain. Let me explain. I have at the end of the day, this is a nested vector I am input. So let me say I have 1, 2 here, and 3, 5 here, and 4, 1 here, and 4 here. I also have some kind of 0. I have 0. I start with 0 and I have 4 elements. I have 4 elements. 0, 1, 2, 3. So I have 4 elements. So this is the outer loop, this is the inner loop. Inside the inner loop there are edges. So, oh, sorry. If we look at our code, let me do both of these. Yes. Okay, look at the code. It's first putting the zeroth index. So we go to the zeroth index and pop it. And we have that zero index and we treating we give the output of 0. It is we start a node. So in the bottom for loop, what we are doing is we pushing all its neighbors. So 0, yes, 1 and 2 neighbors. Again, we come to the top part. That means this part here, we are again looking at the top part. So 2. So when we are popping, it's popping from the upward. So I pop this and go inside the second node. This is the second one. I go inside it. That means 4. So I print 2. Okay. This line. I print 2 before go to the bottom for loop. Now we go to the bottom for loop again. That means 4, 0. And we are looking at the top again. Since it's already visited, we first pop it. Since it's already visited, we not go beyond that. So now we go again to the 4. Now we go to the fourth index. It is only connected to 2. So we are adding those to the stack. We are again looking at the front. So 2 is already visited. So 2 is already visited. So pop it already visited. So we again come to 4. It is pop it already visited. We have 1. From 1 we can go to the 3 and 5 and ahead to the 5. I think you can understand what is happening here. So inside this first for loop, while loop, we are looking at nodes, and this bottom one, we are just adding all the elements of that particular node to the stack, and we are looking at some the top of that thing, and again we are adding that elements for the neighbors. So that is how we can implement depth first search to an iterative method. Now let's go to the breadth first search. So it is also very similar. So white, I make a breadth first search function. To that function I have integer start node, I change in start node and nested vector uh, vector inside it I have integers, so it's adjacency, and I do pass by value because when I call it the function pass by values and the total nodes. I should be total node. And I do the same thing. I make a vector size of vector. I should make a vector with booleans inside it, and I name it as visitor. And inside it there are total number of elements, and all I make forest. I still not visited any of the nodes. And I make queue data structure. And inside it I have integer values, and I name it as queue. So here's the idea. What we are doing is we learn that if the queue is empty, we are done. So while queue dot empty, so until it is not empty, we are looking at the front end. Okay, empty queue, empty char. We are looking at the front, front element. So we are looking at the front element of the queue, as we explained, and queue dot or. So remember, when you're writing pop in a queue, it is popping from the front. So we add an element, we get the first element, that means the front element, and we are popping from the front. And if you want, uh, this is the place you can see out this not element. Okay. So yeah. Next, our bottom fold. Inside our bottom fold, what we are doing is actually this is easy to understand. What we are looking to a neighbors from that particular node, actually the start node or node. Oops, we should have first push our first element to the queue. Here I have to push it to the queue. So queue dot, we should push it to the queue, starting node, starting node, and make it true in visited. The starting node is become true. Okay, this is become true. And now, okay, so we choose node as the front element, and we are popping from the front, and we are looping through its neighbors. We are looping through its neighbors, and each time we are checking whether they are visited or not. Until they are not visited, until they are not visited, and neighbor is not visited, until they are not visited, what we are doing is we make it visit. Make it make another true. So that means we are visiting. Okay, we visited. And then we have pushed it to the queue. So you got push that particular name. We are supposed to particular name. So let me explain this from the scratch. So imagine we have the same kind of adjacency list. So we start with 0. So we have a queue. We have a queue here. And a queue here. We push to it. So push to the front. Push to the back and remove from the front. So we pushed it. Then we push the first thing and we make it visit. So we already visited. So we visit it. So we can write visit it. And until this is not empty. So here it is not empty. So I'm looking through this while loop. And we make a note of this node in front. Okay, I'm adding to the front and I'm popping it. So popping from the front. I pop it. I pop it from the front and I have this 0 and I go inside 0. So this is from the bottom for loop. I go to 1 and 2. And again my front is 1 now and I go inside 1. It is 3, 5. Inside 1 that is 3 and 5. I pop it and my front is 2 now. From there there is 5 and 4 and 0. See, 4 and 0. So 0 is already visited. 4 is not visited. So I add 4 to the queue. So I copy it and go to the third digit. I have 4. It is already visited. Copy and go to 5. Oh shit. I don't have 5 here. So I guess you get the idea. I just make this as an list just 9. So I just wanted to know that how these loops are working, this queue and stack. So this is how the breadth first search is working and the depth first search is working. So hope you have some idea about that than just calling what is happening. So next we are looking at problem solving with the graphs.